You can't see an atom, and you certainly can't put one on a balance. Yet chemistry demands you count them exactly. Too little acid and the reaction stalls, too much and you've wasted it. The entire problem of this unit is counting things you cannot see. This unit is the bridge from grams you can measure to atoms you must count. We fix a mass scale, define a counting unit called the mole, decode formulae, balance the books of a reaction, and finally judge how much product was truly worth making. Master this and every later calculation just falls out. First stop, relative mass. We never quote an atom's mass in grams, the number would be absurdly tiny. Instead, we pick one atom as the ruler, carbon 12, defined as exactly 12 units, and weigh every other atom against it. Hydrogen comes out as 1, oxygen 16. Pure comparison, no awkward grams. 2 cautions the exam loves. Chlorine's relative atomic mass is 35.5, not because half an atom exists, but because it's a weighted average of 2 isotopes, 3/4 chlorine 35 and 1/4 chlorine 37. And for molecule, you simply add the atoms up. Water is 18, 2 hydrogens plus 1 oxygen. Next, the mole, and don't let the name spook you. A dozen means 12, whether eggs or elephants. A mole just means a much bigger fixed number, 6.02 times 10 to the 23, the Avogadro constant. 1 mole of anything contains exactly that many particles. It is nothing more sinister than a chemist's counting word. Here's why the mole is genius. Take an element's relative mass, slap on the word grams, and you are holding exactly 1 mole. 12 grams of carbon, 1 mole. The masses we read on the balance and the particles we cannot see are now linked by a single triangle. Moles equals mass divided by molar mass. Now, formulae. Burn a compound, measure the mass of each element, divide each by its molar mass, and you get the ratio of atoms, the empirical formula, the simplest whole number recipe. Glucose analyzed this way comes back as carbon, hydrogen, oxygen in the ratio 1 to 2 to 1. CH2O, simple but incomplete. Because the empirical formula only gives the ratio, 2 different molecules can share it. The molecular formula tells you the real count per molecule. Glucose is actually 6 of that empirical unit stacked up, C6H12O6. So we find the empirical ratio first, then ask how many of those units make up one true molecule. Now the heart of stoichiometry, the balanced equation. Atoms are never created or destroyed in a reaction, only rearranged, so whatever goes in must come out. Take hydrogen burning in oxygen. 2 hydrogen molecules and 1 oxygen molecule give 2 waters. Count the atoms on each side. 4 hydrogens, 2 oxygens, they match. Those big numbers in front, the stoichiometric coefficients, are the whole reason we bothered with moles. They are a mole recipe. 2 moles of hydrogen react with exactly 1 of oxygen. So if a question hands you the moles of one substance, the ratio instantly gives you the moles of every other. The equation is a conversion table. Last stop, what really comes out of the flask? Reactants rarely arrive in perfect ratio, so one runs out first, the limiting reagent, and it alone decides how much product is possible. The other sits there in excess, unreacted. Always work the calculation from whichever runs out first. The leftover never controls the yield. Even then, theory and reality differ. Percentage yield asks how much you actually got versus the maximum predicted. Losses are normal. Atom economy asks a greener question. Of all the atoms you put in, what fraction ended up in the product you wanted? A reaction can hit a high yield yet still waste half its atoms as byproduct. Here is the whole unit on one page. On the left, the chain of ideas, relative mass against carbon-12, the mole as a counting number, formulae from ratio to real molecule. On the right, the 3 equations that do nearly all the work, the mole triangle, percentage yield, and atom economy. Your drill, convert grams to moles, use the balanced ratio to step to the substance you want, then convert back. That single loop solves most of the paper. The deeper stuff, titration sums, gas volume calculations, redox accounting, builds on exactly this in the units ahead. Get this page solid and the rest is detail.